So what I'm going to do here is I'm going to present you with a couple of problems relating to the logarithmic differentiation material we covered. I want you to pause the video, read the questions, have a crack at them, and then come back and check your answers with the working I'm going to present here. So here you go. 3 questions for you, all relating to logarithmic differentiation, all getting progressively harder the next one you do. So pause the video and have a ping at these. So the first one, y equals 5 to the power of x. Now a key giveaway that we're looking at logarithmic differentiation for this is we have a constant as the base and we have a power dependent upon some function of x. If we have this sort of format, chances are we'll be needing to look at using logarithmic differentiation for it. It just makes our life a lot easier. So in this order, what I want to do is take natural logarithms, ln, of both sides. So natural logarithm of y equals ln of 5 to the power of x. Now this side here, what I'm able to do is use my rules of logarithms and bring the x down. So I'd have x times ln of 5. Now ln of 5 is a constant. If you put that in your calculator, you'll just get a number that comes up. So essentially, this is of the same format as if I had something written as a times x. So what I'm now able to do is just work my way through it, treating this as a constant, and I can take it from there. So ln y on this side, I end up with 1 over y times dy by dx. Remember, y is still some function dependent on x, so we have to still do the dy by dx when we differentiate it. And that's going to equal just the ln 5, because that's all that's left. What I'm now going to do, shift the 1 over y across here by making it a times. I then end up with dy by dx equals ln of 5 all multiplied by the y. I'm then going to substitute in for the y from right back at the start. I'm going to get dy by dx equals, I'm going to write 5 to the power of x first times ln of 5. It just avoids any confusion with the 5's next to each other. So there you go. That is the derivative of that function there. Second one was y equals 2x to the power of x. Again, I've got some power. Now, the base is an x, so the base is a function of x, but it's a power where it's also a function of x. So it's a function of x to the power of a function of x. That sort of format, again, we could look at and think this would be much easier using logarithmic differentiation to separate the parts out. So I'm going to take natural logarithm, ln, of both sides. So I get ln y equals ln of 2x to the power of x. Again, use my rules of logarithms to bring it down, and I get x times ln of 2x. So I've got ln y equals x times ln 2x. I'm going to differentiate both sides. So for this one, I get 1 over y times dy by dx. And for the right hand side, well, I've got 2 products there. So what that means is I have to bring the product rule into play. So if I start doing that, what I'll end up with is ln of 2x plus x times the derivative of ln 2x. So that gives me 1 over 2x times the derivative of the 2x, which is just 2. What I'm then going to do, bring the y across. So I'm going to end up with dy by dx equals that y times, then what's in the bracket that I'm going to make. So I've got ln of 2x plus, well, this one here, if I'm simplifying this, I'll end up with x times 2, so 2x on the top, 2x on the bottom, so it's then going to be plus 1. And again, at this point, substitute back in for the y, so I can say dy by dx equals the 2x to the power of x, open bracket ln 2x plus 1. So there you go, logarithmic differentiation has broken it down, made it a heck of a lot easier, and allowed me to do it in a much simpler format. The third one was this function here, so y equals x squared times the square root of 7x minus 3 all over 1 plus x. Now again, this is a lot more complex looking than we want it. So if I take the logarithms of both sides, i.e. ln of both sides, I can split it up using the rules of logarithms, and I can then make it easier for myself. So I'm going to start by taking ln y on the left, and that's equal to ln of x squared. Now what I'm going to do is I'm going to write square root as a power. So it's going to be x squared times the 7x minus 3 to the power of a half. Remember, when we're taking derivatives, having it written as powers helps us a lot more. All over 1 plus x. Now this side here, again, I can split up using the rules of logarithms. What I'll end up with is ln of x squared plus ln of 7x minus 3 to the power of a half, take away ln of 1 plus x. So there you go, I've split it up that way, but I can then go one step further by using the rule which involves a power. So I can then rewrite it as 2 times ln x plus a half ln of 7x minus 3 take away ln of 1 plus x. So I know that's my right hand side, there's my left hand side, the ln of y. Now I can just differentiate both sides. Left hand side here will give me the standard one I'm used to at the moment, 1 over y times dy by dx. What that's going to equal on the left hand side, I just go through each term on its own and calculate the derivative. So it's going to be 2 times the derivative of ln x, so it's going to be 2 times 1 over x. It's then going to be plus a half times the derivative of ln of 7x minus 3, so that's going to be times 7 over 7x minus 3. It's then going to be take away the derivative of 1 plus x, so ln of 1 plus x, which it gives me 1 over 1 plus x. So what I can now do, bring the y across and simplify all of this. I'll end up getting dy by dx equals y, bracket 2 times 1 over x, so 2 over x, plus 7 over 2, bracket 7x minus 3, take away 1 over 1 plus x. Now quite a lot of the time it will be happy enough for that. It may be a little bit nasty and ask you to put it all over. A common denominator is 1 fraction, but at this stage, in this example, I'm happy for us to leave it like that. The only thing I will say is we want to get rid of the y here, so I'm going to substitute back in for it. And I'll end up with dy by dx equals my original function, x squared times the square root of 7x minus 3 all over 1 plus x. And that's then going to be multiplied by this derivative here. So I end up getting 2 over x plus 7 over 2 bracket x. So 2 bracket 7x minus 3 take away 1 over 1 plus x. So there you go. I've got the derivative there. Now that would have been great fun to try and use one of our other rules of differentiation, for example the quotient rule, which would then also combine the product rule and the chain rule, but in this case all I've done is split it into one line where I've used the rules of logarithms to break it up and make it a lot easier for myself. If I'd stuck with the quotient rule, chain rule, product rule combination, I'd have taken a heck of a lot more time and a fair few more lines to be able to do it. So logarithmic differentiation comes in handy in those scenarios and makes it a lot easier for us to calculate the derivative of slightly more complex functions by breaking it down into easier ones for us to work with.